So yeah, I'm going to tell you a little bit of some of the machine learning methods we've been developing in our effort to search for new superconductors. I'm going to talk about 2 projects, and you're going to see by the list of authors that there were many people contributing. A large number of these people are actually students and undergraduate students, which helped with some of the data collection I'm going to tell you about later on. I'm going to talk about, in the first part, about a method called ultra-fast potentials. These are machine learning potentials to describe the energy landscape, which I'm hopefully convince you that using a B-spline basis and regularized linear regression, that we can fit very accurate potentials, we can fit them very fast, and we can evaluate them very fast, hence the name. In addition, I'm going to show you that they're also easier to interpret, and that helps us to understand if there are any holes in the energy landscape, etc. In the second part of the talk, I'm going to discuss how we're going to use a very different machine learning technique called symbolic regression. We're also going to talk about random forest and neural networks as a comparison. And we're going to use a method called data augmentation to learn the superconducting critical temperature from the same parameters that Allen and Dines and Macmillan identified being important for superconductivity. And so this is essentially repeating the work of Macmillan and Allen and Dines in a modern framework, and show that computers can actually do the work more efficiently and with a sufficiently large data set, give us good equations, really analytic equations, just like Allen and Dines, for predicting TC. I want to acknowledge some of the team members and collaborators also here. And I want to also point out that a lot of the work I'm presenting really grew out of an IPAM program. IPAM stands for Institute for Pure and Applied Mathematics, an NSF-funded math center at UCLA, where several of my students and I have spent 2 semesters talking to mathematicians, computer scientists about machine learning and other techniques. I also want to emphasize the quantum theory project, as well as the supercomputer we have at UF called HyperGATA. Everything at the University of Florida is called AGATA. And we have funding from the US Department of Energy and NSF. So I want to say a few words up front about machine learning in material science. And this is just giving you an overview of some examples of where this becomes important, because I don't know if everybody in the audience is as familiar about machine learning and AI methods. So there are techniques called supervised learning. Supervised learning are techniques when you actually give the computer the data and you give it examples of the predictions for the data. So it's essentially something like a regressional classification where it says, here's some data, learn on these predictions, do a good job, and then we apply it to unseen data afterwards. In general, most type of machine learning deals with big data. So we'd like to have lots of data. The more complex our models can be. And we can do that in material science when we have high throughput screening for properties, learning on the NOMAD or Materials Project database. When we develop surrogate models for structure exploration, these can be big data problems. However, often we don't have big data. Especially in the field of superconductivity, the number of superconductors is certainly not in the hundreds of thousands yet. So we're dealing with small data sets. And then there are other techniques which can be powerful, which are a little more rigid, not as flexible as neural networks, more rigid, like, for example, symbolic regression, where we try to put equations together out of mathematical symbols and operations. And that's the second part in the talk I want to tell you about. Another type of machine learning, which is often in the machine learning literature considered the really true type of machine learning, is when we don't give the computer the answers to what we wanted to learn. In other words, we treat it like a baby, put it in the world and say, go figure it out. See if you can learn what we're speaking, see if you can learn what's happening around you. It's called unsupervised learning. And so that also is a method that can be useful in material science. For example, if you look at data sets where you don't yet know what you actually try to do with it, where you want to classify it and see, hey, can we group it in different categories, etc. And one example for that is identifying new configuration in a molecular dynamics trajectory and say, hey, here the algorithm found something it hadn't seen before. Classifying them is unsupervised learning. So in the first part of the talk, I'm going to talk about machine learning of energy landscapes and the relation of that to the question of discovering room temperature superconductors is really that we need to, as a first step, often predict what crystal structures are actually stable. The reason why that's even more important in the high pressure field is that we don't have quite the large databases of hundreds of thousands of materials and their structures at arbitrary pressures. So there's a lot less data under pressure. And ambient conditions, that's a little better. Like I mentioned before, this came out of two IPAM programs, the one in 2017 and the one in 2019, and the one in 2019. Can you guys see my mouse? Yeah. The person who's really led that effort was Stephen Chi, who was a graduate student back then and is now at NASA Ames. We also work closely with Matthias Rupp, a computer scientist at the University of Constance in Germany. And then there are several other collaborators, and that list has actually been growing quite a bit in recent times. So I don't have to explain to this audience much about energy landscapes other than we really normally describe some with density functional theory. That's often when we use the right approximation sufficiently accurate to give us a ground state structure, but we could use other quantum mechanical methods just as well. But these methods are slow. They're slow, time consuming, they require a lot of compute power. An alternative way is using empirical potentials, and those are just ball and spring type models where we integrated out the electronic degrees of freedom, and we have some approximate version of that. The advantage of these empirical potentials is that we can really rapidly search through structure space with those methods, but they're highly inaccurate and usually don't give you anything particularly useful, especially in regimes where they weren't fit for, like under high pressure. And so, but if you have interatomic potentials, you can calculate phase diagrams very rapidly. Here's an example where we applied our genetic algorithm to the aluminum, nitrogen, oxygen phase diagram using an empirical potential to test that potential. How good is it actually? We can calculate all kinds of materials properties, phonons, elastic constants, and we can simulate dynamical systems like melting and chemical reactions, etc. So in other words, having these surrogate models and interatomic potentials can be very helpful. The question is how we make them accurate. And so we have to go from the empirical potential type to really to the machine learning potentials, which have a lot more flexibility built in. And so empirical potentials are things like the Lennard-Jones potential illustrated here, where the energy as a function of distance, forces are just derivatives, etc. And they're more complicated, complex empirical potentials, which we take inspiration from to design the machine learning potentials we actually want to build. In machine learning potentials, there is a large spectrum of what can be done on the machine learning method side itself, as well as on the descriptors. And I'm going to tell you specifically about the methods we have developed with a goal to be flexible and fast. So that resolution looks a little annoyingly low, but we'll deal with that. So I want to first mention that there is an accuracy speed trade-off. So we already mentioned the DFT calculation being highly accurate, very slow. And I'll show that in that plot where I show error on the y-axis and computational cost on the x-axis. DFT is on the top and the bottom right here, highly accurate, extremely slow. Empirical potentials like the Lennard-Jones potential, etc., or the Morse or embedded atom potentials are typically extremely fast. We actually normalize the cost often to Lennard-Jones and see how much slower is a method relative to Lennard-Jones. And so we put 1 as the speed for the Lennard-Jones here. Bars in the way here. Up here, and we refit the Lennard-Jones on a specific materials data set. This is tungsten data by Garbozzani, 10,000 configurations. We use 2,000 for fitting, about 8,000 for testing. And when we refit the Lennard-Jones potential on that data, we get a pretty large error of energies and forces. The Morse potential has a little more complexity, does a little better in its error. And we also plot here an EM potential, which we didn't refit, because not because we didn't try, but because fitting empirical potentials is sometimes more of an art form because it's a highly nonlinear optimization problem. I also show you on that same plot where the modern machine learning potentials show up. And so here's the gap potential on the right, so it's a little bit of one of the slower ones. The spectral neighbor analysis potential, SNAP and its quadratic variant, and the moment tensor potentials. And as you can see, they all do somewhat similarly. They differ quite a bit in speed. And what I'm going to talk to you today about is these potentials on the bottom left in that Pareto plot, which have moderately small errors and are certainly fast. They are about as fast as these empirical potentials I've already talked about. These are the ultra fast potentials, and I'm showing you here the 2-body version and the 2- and 3-body version. And you can see that they're about an order of magnitude faster than the MTP, and that we certainly can gain about 5 orders in speed relative to DFT if we use them. So I'm showing you later an example how we can use these to actually explore crystal structures with more complexity. Developing that potential, we started with 4 main goals. we wanted to have a systematic expansion to be able to make it more and more accurate for systems where it's required. So we start with a many-body expansion of the energy landscape, systematically improvable. We wanted a real space description of the structure. We don't want some feature vector like SOAP, etc. We wanted a description which really directly takes the distance between atoms as input. And the motivation for that is twofold. One is speed. All molecular dynamics codes use that as an input, so you don't have to calculate a feature first. And it also makes interpretability of these potentials easier, because often we can think of interactions of atoms as a function of angles, distances, etc. So a real space description helps there. Then our contribution here really is that we want to represent these many-body potentials by a compact and smooth basis set. Those are the so-called B-splines I'll tell you about. And compact is important, that every basis function only spans a finite domain that significantly improves speed and memory efficiency. And it also helps us to be flexible in the resolution. Using more basis function does not change the cost. And finally, we turned this problem through a little bit of mathematical writing into a strongly convex optimization problem, which means it's a problem which is really like a quadratic problem, only one minimum, and you can go to that one minimum in a very small number of steps, in principle in one step. So that flexible spline potential I'm going to tell you about is accurate, fast to fit, fast to evaluate, and easy to interpret. Well, let's talk about these four guiding principles I have in a little more detail. So we want to start out with a many-body expansion of the energy landscape. So we're going to take the energy and write it as a sum of on-site terms, so atom-centered terms, then pair terms, three-body terms, four-body terms, and so forth. And that expansion, in principle, should work. There is no mathematical proof that it's transferable between all configurations in a material, but that's widely believed to be true, at least over a certain domain, and we'll make that assumption here too. We certainly truncate that expansion. Right now, we have a version which actually works up to n-body, but we've only tested it up to 4-body. And the version you can download online works already up to 3-body, and it's surprisingly accurate. The advantage of that expansion also is that you can look at those 2, 3, and 4-body terms directly and figure out what's the interaction actually like. So I'm showing you here an example for lithium germanium on the bottom, where I show you the 2-body and the 3-body potential. And you can clearly see the 2-body potential has a repulsive part. There's a minimum, there's a little wiggle in there, so something interesting happens, and then it goes to 0. The 3-body part is given as a function of distance and angles between, in this case, I'm only showing the lithium germanium one, lithium being a center and then one lithium, one germanium neighbor. And you can see repulsive regions in those angles and attractive regions. And that's important for materials which are, for example, somewhat covalently bonded, etc. So interpretability is an important contribution. So the basis we're going to use is a spline basis. We're using a specific spline called the B spline. B stands for basis splines because they are very compact representation. And so here's an illustration of what they look like. We're looking at a central atom and looking out to certain distances, putting these basis splines down, which are illustrated in here. And these basis splines have a finite domain. They go up to 4, covering up to 4 knot points. And that means at every distance, you only have to evaluate 4 basis functions, independent of how many splines you use. So that local support means that the cost does not scale with the number of basis functions. So higher resolution, there's no change in cost. The basis splines we use are cubic B-splines. We need to make sure that we have a first derivative of forces that is smooth. That's very important for MD simulation and relaxations. And the second derivative is just continuous, so that it has cusps in it. And that's important for phonons and elastic constants. So that makes it a memory efficient and as well as a speed efficient basis set. When we plug that into that expansion I showed you earlier, I'm showing you here only the 2 and the 3-body term. You can immediately see plugging in the 2-body potential, for example, in here, it's just the basis functions called capital N times some coefficients in front of it. You can immediately see that the final equation is actually linear in those coefficients Cn and CLMN. That's very important because that means we can use linear regression to solve that. And that's exactly how we do it. It's also easy in that implementation to implement physical boundary conditions. What happened at short distance, what happened at long distances. And that avoids the difficulty neural network potentials often have, where they can have holes at certain configurations. We don't have those. So linear regression. We do one additional step. We do something called regularization. That enforces these potentials to be smooth. And it also and forces them not just to have smooth curvature. So we're actually penalizing the local curvature of the potential, and we're penalizing the many-body terms beyond the two-body terms to be as small as possible. We want most of the work to be done by the pair potential, which takes care of the repulsive part and then goes to zero out there. This is called Tikhonov regularization for strongly convex optimization, and they're very efficient to solve. It's a direct minimization, one step, or you can do it iteratively if you want to. That's a little slower typically, but not a big deal. The optimization of these potentials on a laptop, my students did most of these calculations on a laptop, takes minutes at most, even for large data sets. Let's talk about some of the benchmarks. So I've already showed you in that initial plot the energy and force error. So the energy and force error, when we just have the two-body potential, is actually much better than any empirical potential. Looks useful, but not as good as the many-body potentials, but it gets as good when we include the three-body term. We have not on this data set tried the four-body term, but we expect to get significantly slower and maybe slightly better. So there may be a trade-off that you have to decide how many terms you want. I'm showing you on the right here the phonon spectra, so that gives you an idea about how the forces really work over the whole Brillouin zone. And you can see that the EM potential, for example, has some difficulty here at the endpoint. The Morse potential does actually surprisingly well, and our two-body potential shown in the top plot does very well for the phonons. We compare to other potentials, machine learning potentials, and to DFT also down here, and you can see that the UF potentials 2 and 3-body do a great job of reproducing the phonons of that relatively simple system. We also looked at some data which was not really part of the training, because we, so for example, the elastic constants and surface energies and the vacancy formation energy were not directly trained on. And the two-body potential in that spider plot is shown on the top, the three-body potential down here. And so we're doing significantly better than Leonard-Jones, which overestimates almost all of these parameters, and we do better than Morse, which underestimates a significant number of those. And we do certainly also better than EM, and comparable to the moment tensor potential, and somewhat better than SNAP, comparable to QSNAP and GAP, as you can see. And so the three-body potential looks nearly perfect. It nearly is a circle with a radius of 1, so in other words, no error. We also did some really out of sample testing case, that is looking at the melting point. There is no data in that data set of amorphous or liquid configurations. And so we did not expect that to do particularly well for any of the machine learning potentials we fit. And when we do that, in that video here, so it's just illustrating how we do that. We have a liquid and a solid part, and then turn the thermostat off at some point, and then see what the system equilibrates to. We find that the two-body potential slightly overestimates the DFT melting point, but and the three-body term improves that. These predictions are significantly better than some of the other machine learning potentials, and some of the other machine learning potentials we tried actually couldn't simulate the melting because they had holes in the energy landscape and they diverged. They just simply blew up. I don't want to name anything specifically here, because part of the reason that they didn't do so well is because we specifically used a small data set of only 2,000 configurations. More configurations help these other potentials probably improve that and not have these holes. Okay. Just to show you a couple other results, we applied the method also to the mLearn data set, which is a data set for elemental energies and force configurations, and compared to the same type of machine learning potentials. Here, light color, so light yellow, means good. Darker colors means the errors are a little larger. And you can see the UF3 is on the top, and it does essentially comparable to all these other machine learning potentials illustrated here, and it does slightly better than a number of them. So it's certainly very competitive, and it does it at a reduced computational cost. Let me show you an example where we actually showed one potential use of this potential, and that is where we look at the lithium germanium system. We had previously done a genetic algorithm with DFT on lithium germanium to figure out what the ground state structures were. And here's just an illustration how a genetic algorithm works. You start with generating structures, more and more structures, and update the convex hull and figure out what structures are actually ground state structures. And so we used that data set and actually split it up in an interesting way, where we said, let's only train on small unit cell structures, because those are cheap to calculate in DFT. And then let's see how it extrapolates to large unit cell structures. Is it actually transferable? And so we train on unit cells with up to 8 atoms, and we apply it for the remaining 3,500 samples we have, which have larger unit cells up to 20 atoms in them. And if you look at, I'm showing you here just the energy error, but the force error does something similar. On the small unit cell where we train on, we get an error, an RMS error of 7 milli-electron volt per atom, which is excellent. And when we go to larger unit cells, we get something like 27 milli-electron volt per atom, which is still very excellent and certainly very useful for genetic algorithm if you want looking for the low energy structures down here, as you can see. You can use this method to eliminate a ton of structures where you don't have to do DFT calculations on and accelerate your search probably easily by a factor 100 or more. And you can go to larger unit cells than this because this essentially costs nothing compared to DFT. I mentioned a couple types interpretability. And this is one of the things which is very important in machine learning. We'd like to have machine learning models which we can understand what's going on because we want to extract some physics out of it. And here are the pair potentials for the lithium germanium system. And you can see, first of all, they have a repulsive contribution. So you will not get atoms overlapping in those methods. They have a minimum and they have some wiggles on them. So those wiggles are somewhat interesting and maybe good chemists can tell us why there are some sort of inflection points in there. We can also look at the three-body terms, and there's a bunch of them here, and you can see which angles certain pairs of atoms prefer or do not prefer. I'm not a chemistry expert who for that system can now tell you what that indicates about the bonding character, but you at least have the chance to really look at that easily, which is very hard in a gap or a snap potential or in a even in neural network potentials, etc. So I hope to have shown you that we have a method which we call ultra-fast because it is faster than any existing machine learning method we have tried. And it's as fast as some of these empirical potentials and significantly more accurate. Easy to train, regularized linear regression, and easy to apply. And you can actually download that today and try it out yourself. We have a bunch of tutorials there, and we're happy to answer any questions you may have. We also have the data sets available for the machine learning. The mLearn data set is available on GitHub. That's not ours. And then we also have our own data sets for lithium germanium, etc. available. Well, let me, in the remaining few minutes, talk about the second part where we talk about symbolic regression and actually come back to the topic of superconductivity of this workshop. So slightly different group of people which contributed to that. And the goal here is to learn an equation similar to Macmillan and Alan Dines and see if a modern machine learning algorithm can do as well or better than Alan and Dines and Macmillan did. So we all know and love the Macmillan and Alan Dines equation. So here's the Macmillan part underlined in blue, and Alan and Dines modified it by adding or multiplying two factors to it to fix some of the shortcomings of the Macmillan equations. Here are those two prefactors, and so what I'm going to show you first is learning the whole equation in a simple way, just using Alan and Dines' data. And then I'll show you how we can improve on the actual Alan Dines equation by learning two new prefactors instead of the original one, which improve especially the prediction for hydrides. We're using the same descriptor as Alan and Dines did, the electron phonon coupling strength lambda, the logarithmic frequency, omega-2, the second moment of alpha squared f, and the Coulomb pseudopotential. And Alan and Dines came up with those descriptors and showed that they work well. We've actually tested some other descriptors, and whenever any other combination we tried is actually worse than these four descriptors. So Alan and Dines, without computational power as we have today, did very well. They studied 3 alpha squared f's. They studied the Einstein model. They studied lead and mercury alpha squared f's. Those were the 3 model systems to develop their equation. They used data for 29 materials to fit all their coefficients and come up with their equations. And so we're going to use the same data and now going to do something slightly different first. First, we're using Alan Dines' data and use symbolic regression method called CISO. The way it works is you start with the descriptors you want to use. Omega, log, mu star, and lambda is what I'm illustrating here right now. As I mentioned earlier, we tried all kinds of other combinations, and these 3 alone actually turned out to be the best. Omega-2 doesn't really help much in the way we did these calculations. Then you use a bunch of mathematical operations, and in symbolic regression, you take those symbols and combine them with those operations iteratively. So here's, for example, you can add mu star and lambda. You try to preserve units in that, by the way, to make sure that you don't end up with equations that are physically meaningless. Omega log times lambda, and so forth. At the next level, you combine the previous levels in any random way you want, and you do it systematically. You actually write out all possible combined expressions out in the CISO code. So, and at the third level, you're running out of steam in that method. You usually get millions of expressions, and the code usually says it can't go any further because the next level is 100 billion terms or something like this. You just simply can't handle those. Once you have that, you take these equations you have, plug in your data, and do a scalar product between your prediction and the results of those equations, and pick a subset of the best and move on. We also had to do some additional step because the CISO code was not perfect when it looked at units. So we had to fix that. The nice thing about also this method is you can put in physical constraints. We put in when lambda goes to 0, TC goes to 0. We also said, well, the critical temperature should be strictly positive, 0 or positive. We put in that the temperature, the critical temperature remains finite, that it continuously changes with the variable, that it remains real, and it's monotonically increasing in lambda. We didn't put in the square root behavior, and we were thinking maybe the algorithm finds it, maybe not. So we end up with about 6,000 at that point equations, and we looked at the lowest 100, and here they are in light blue are the lowest 100 curves. The thick blue here is the best result CISO gave us. And then we compare that with Allen and Dines. Here's two Allen and Dines curves because we looked at two different values of omega 2 bar to make sure what is the typical range Allen and Dines would predict. We don't have omega 2 bar in our prediction here. And so the equation we get looks like that. One numerical coefficient and a really simple equation. And it does as well on the training set here. Here's the training set. Here are the leave one out cross-validation errors. And it does as well on those as Allen Dines and does, and it's better than Macmillan, right? So that was the point of Allen Dines to improve on Macmillan. Our equation is significantly less complex, has no omega 2 bar dependence, and a comparable accuracy to Allen Dines. And we then applied it to out of training testing data, and it does again similarly well as Allen and Dines. But there's a couple outliers, which are materials which either are layered or have somewhat of an anisotropic alpha squared F. So what we noticed, however, is it doesn't show the square root behavior. It actually goes linear for large lambda. And that is because the data set we have doesn't show the square root behavior either, because it's much too small of a range. I mean, the TCs are really tiny. And so we thought, how can we improve that? And so one way of improving it is actually to augment the data by data which is calculated or by data which is made up. And so calculating alpha squared F is somewhat expensive. And we did that. We had a good postdoc, Yun Li Kwan, which helped with that. And we came up with 50 materials for which we got alpha squared F. We calculated for a number of materials alpha squared F. We went through the literature and simply scanned in alpha squared Fs from paper. Or in some cases, when we didn't get the alpha squared F, we just took lambda, omega log, omega 2, and mu star from the literature and the TC calculated and put that in our data set. We ended up with 50 materials in total. A bunch of hydrides and a bunch of other materials. And we already talked to a couple of people in the audience. There's way more calculation you have done. We would love to try those out as well at some point. When possible, we calculated for the alpha squared Fs also TC using a range of mu stars, because that's something that's completely undersampled in Allen Dines' data set. But 50 is still a teeny tiny data set. We went from 29 in Allen Dines to 50. Next thing is we do data augmentation, where we fake the alpha squared F. We just create multimodal Gaussians. As you can see here, they actually do look somewhat like the normal alpha squared F. And we can get, with the artificial Gaussian, a much better sampling of those parameters. And then instead of now learning the full equation, we're going to just learn the prefactors for the Macmillan equation, just like what Allen and Dines did. I'm going to show you results next where we did that with symbolic regression. We also use random forest and neural networks to show how well they do, because now the data set is large enough to do. By the way, the hydrides we left out for validation, because that was the goal of the work, to figure out, can we improve the Allen and Dines prediction for the hydrides, where Allen and Dines systematically underpredict TC. Here are the results. So as I said, we take the Macmillan form and we multiply it with two prefactors. The prefactors have a similar complexity we get as Allen and Dines. And what we see is Allen Dines results on the left, symbolic regression is on the right. We do very similar for the non-hydride materials. There's really not much of a change. We have the same RMSE. We do significantly better on our artificial Gaussian. We have a lot of them, and they go up to 400 Kelvin in TC. So I think we were kind of anticipating that some of the results really get there someday. And for the hydrides, we do also significantly better down here. So that's really the main part of that equation. It improves on Allen and Dines and gets us a much reduced error, especially for high temperature superconductors. So we think this equation really could replace the Allen-Dines equation in your frameworks when you calculate TC based on the other parameters. The other thing this type of machine learning shows that putting in physics really can help you come up with robust machine learning methods, and also that we can do machine learning in a step-by-step basis. That's the next step in machine learning would, for example, be, can we try to learn lambda and maybe omega log and omega 2 bar from other underlying data? And that we have not succeeded with yet. And we've heard from other people that that seems to be a very hard problem. Okay. I'll skip the benchmark against neural networks and random forest. They don't have that interpretability. You can't see if it's square root. Random forests also have a problem that they're actually not very smooth by construction. So I think the equation, the symbolic regression is actually very powerful here. So, so in summary, we developed a set of equations here based on the Macmillan equation, which improves the TC prediction, particularly for high temperature superconductors and hydrides. So I'm out of time pretty much. I want to make sure there's time for questions. So I hope to have convinced you that machine learning can be very powerful in our field to accelerate the search for new superconducting structures by approximating the energy landscape, and also that it can potentially help with finding new superconductors based on other materials properties, which hopefully are easier to learn than TC itself. Thank you very much for your attention.